A very good evening to all. My name is Hitesh Jindal, and I'll be taking your webinar today. We'll be discussing the modern physics part of physics today. Right, so we'll be delving into the important concepts, the core concepts, the previous year questions which we have got in the last 2 years, right? 2024, the paper I'll be discussing, the questions related to modern physics, right? The mark distribution will be saying, and we'll be looking at the overall importance of the modern physics for the coming CBSE board exams. So I request you to please turn on your cameras for the session to be more effective. All right, so let's start with the session. So what do we understand by the modern physics overall? Mehak, we have Mehak here, Janam, Mohammed. So you'll be having your CBSE boards in a few days. So I think you must have gone through the entire physics syllabus and now on the revision path. So modern physics is considered as the most scoring part in the physics syllabus, in the 12th physics syllabus, right? So what are the topics which we have in it? Can you tell me? Anyone? Yes, correct, Jasim. That's dual nature, nuclear physics, semiconductors, and atoms. So we have 4 chapters from our NCRT, right? So what is in what is modern physics all about is, you see, we have 2 types of physics, right? One we known as classical physics, right? Classical physics, also known as Newtonian physics, which is applicable, which is applied to our everyday objects, right? Everyday objects have dimensions. You see, we have moderate sizes of the objects, right? Right. But you see, we have astronomical objects also, like black holes. So with respect to black holes, we don't apply classical physics. So classical physics is applied in relation to the everyday objects we see around us, the cars, the vehicles, right? The tables, the chairs, right? We ourselves, right? We are also objects, we are also bodies in when physics is concerned, right? So that is classical physics. But what happens in modern physics, this element of quantum comes. The concept of quantum, right? The concept of quantum comes, right? So in dual nature only, we get this idea of quantum. Can anyone tell me what do you mean by quantum in terms of energy? Let's say energy of a radiation. Is energy of a radiation a quantum quantity or what? Let's have an interactive session, right? So I want your responses. Yeah, small packets of energy is the same, right? Good, right? So what do you mean by quantum? Having discrete values, right? Quantum is something having discrete values, right? It cannot take continuous values, right? So it has discrete values. The values are in like this steps, right? The way we have learned in the charge on a body, right? We have learned that the charge on a body is always integral multiple of E, right? So that what we learned, that charge is quantized, right? So that is the whole meaning of this word quant, right? Quantum, right? So energy is quantized, right? So in terms of radiation also, what we study in dual nature, right? So it says that radiation is what? In radiation, right? Let's say, so we have learned this in photoelectric effect. Let's say we have a metal surface, right? And if the radiation is coming, radiation is incident on it. So it is not a continuous form of energy, right? The energy is striking it just in the form of packets, right? Just like we throw balls on something, right? Just like we strike balls on some surface. In the same way, so balls are what? Discrete quantities. We can calculate balls, right? We can have one ball, two ball, right? So we can have one packet of energy, two packets of energy, right? We cannot have 1.2 packets of energy, right? We cannot have 1.2 photons. We can have two photons, three photons. Getting it? So that is the meaning of quantum, right? So this has changed the way we see our universe now, right? So modern physics has this concept of quantum inside it, right? So there are various phenomena which cannot be explained by this classical physics. So that's why we come into the realm of quantum physics, right? So that is all about modern physics. So as quantum physics or quantum mechanics is applied to what? What size of particles it is applied to? It is applied to atomic or subatomic particles, right? So atomic particles are what? Atomic particles are electrons, right? Protons. So electrons we have, protons we have, neutrons we have. So to these particles, when we study these particles, these dimensions, like particles of these sizes, then that physics is known as modern physics, right? So that is why what we have in here, the chapter of atoms, you see. So in this modern physics, what are the topics which will be covering? The atomic structure, right? The nuclear physics, subatomic particles will be studying, right? And also in this quantum mechanics, we have this thing known as wave particle duality. You see, some concepts are there in modern physics. One concept I have told you is the concept of quantum, right? That anything having discrete values, anything taking discrete values is considered to be a quantum, right? Then we have this concept of wave particle duality. Wave particle duality. As I said, that radiation is what? Light. Light is a radiation, right? So light is a wave and light is a particle also. So light is made up of photons. Photons are considered as particles of light, right? So both the behaviors the light is showing. Similarly, in dual nature, we have dual nature of radiation also and matter also, right? In our entire universe, what we have? Only two things, right? In our entire universe, we have what? We have matter and we have radiation, right? Radiation we can call as energy, right? So we have matter, we have radiation. So, and nature is symmetrical, right? Nature is what? Nature has symmetry. You see, we have symmetry in our bodies. right? So nature has symmetry. So de Broglie, you understand de Broglie, you must have heard of it. I'm just giving you the basics of it, right? So we have this de Broglie. So what de Broglie thought? De Broglie thought that as radiation is having dual nature, as radiation can behave as particle also, can behave as wave also, then matter must also be having dual nature, right? Matter must also be behaving like, obviously matter is made up of particles, right? So matter must have this particle nature, but matter also has wave nature, right? So can anyone tell me what is the physical quantity associated with a wave? Anyone tell me what is the physical quantity associated with a wave? It's the wavelength we calculate, right? If something is having a wavelength, then we say that it is a wave. So that's why this concept comes of de Broglie wavelength, right? This de Broglie wavelength concept comes, right? And what is the quantity associated with the particle? Now you can tell me. Please let me know. No, not frequency. What do you think, Niranjan? Sachi? What do you think the physical quantity associated with particle nature? What it is? Yes. Yes, Syed. It is mass and velocity, right? And what that quantity is? That quantity is momentum. Momentum, right? Right. So what is de Broglie wavelength then? Then de Broglie wavelength becomes what? Lambda is equal to h by momentum, right? Momentum shows that obviously matter has particles, so it has particle nature, and then now lambda is showing that matter has wave nature also, right? So this is all about this modern physics, right? I am talking about the modern physics part. And modern physics has this wave particle duality concept, this quantum concept, right? And also this new types of materials we have, right? This solid state physics, we known as a solid state physics. And this solid state physics comes under this semiconductor electronics, right? This semiconductor electronics comes under solid state physics, right? In semiconductors, what we achieve is we achieve better ways, right, to control the flow of electrons, right, in semiconductor electronics that we study by various devices, right? Diodes, transistors. In our syllabus now, we only have diode like p-n diode, junction diode, not transistors we have, right? So these four chapters are in your modern physics. Very scoring chapters, right? And short chapters, not taking much time for revision, right? So with regards to the marking scheme, let me tell you, yesterday also I have told you that dual nature of radiation and matter is having 4 marks, right? Atoms is having 4 marks, nuclei, right? I'll write down again, right? Write down. You see, so dual nature of radiation and matter is having 4 marks, right? In your exam. I'll be showing you 2024 exam and we'll be looking at questions coming from modern physics. So you'll get an idea that how the questions are being framed. Got it? Now then we have atoms, not atomic models, right? We have this chapter known as atoms, right? Atoms is of 4 marks. Then we have this chapter called nuclei, right? That is also 4 marks. And the semiconductor electronics is of 7 marks, right? So in total, our modern physics comes out to be how much? It is 19 marks, right? Our paper is of 70 marks, right? So it is more than you see. It is more than 25%, right? So one-fourth of the paper is from modern physics. More than, you can say more than 25%, right? So it is very important from the examination point of view. Whether you are preparing for competitive exams also, whether JEE or NEET, then also it is very important. Got it? Any question till here? Okay. So now can you tell me the core concepts of dual nature of radiation and matter? What are the core concepts? Two core concepts to tell me. Anyone? Yeah. In the previous webinar, we talked about the importance of core concepts, right? Which have high probability of coming in the exams. So what are the core concepts from this dual nature of radiation and matter? Can anyone tell me? So herein we have, yes, H by P, right? Right, photoelectric effect, good, right? So in this dual nature of radiation and matter, you must have, right? You will have a question from photoelectric effect, right? You will be having a question from it, photoelectric effect. Plus, second topic is what? Second topic is de Broglie wavelength. De Broglie wavelength, right? What about atoms? Now, earlier there was Davison and German experiment. Now it is deleted. So you must be aware of the deleted portions, right? What about atoms? In atoms, we have Bohr's model, right? Rutherford's model, the drawbacks of Rutherford's model, and then the Bohr's model, right? So, and most importantly, the emission spectrum, right? The hydrogen spectrum, the hydrogen spectra. What about nuclei? The important concept is related to the density of the nucleus, right? Density of the nucleus and the binding energy concept. The binding energy concept and the related concept is mass defect, right? I'll be showing you a slide which is having these all topics, right? In short, right? Then about semiconductor electronics, we'll be having the concept of intrinsic and extrinsic. So this difference you must be knowing that might come, right? Extrinsic and intrinsic. What is the difference between them? And then we have PN junction diode, right? PN junction, the concept of PN junction and the related concepts, right? The PN diode, the junction diode, right? So these are all the important topics we have in modern physics, and questions will come from these topics, right? So you see, I have already written here the photoelectric effect. So this is the important topic we have, right? In that, what we have, the definition part, like what is photoelectric effect, the threshold frequency concept, the work function, right? The Einstein's equation, right? Can anyone tell me the Einstein's equation? What is the Einstein's photoelectric equation? What it relates to? The maximum kinetic energy is equal to what? The energy of the incident radiation minus work function, right? So this is the photoelectric Einstein's equation, right? Very important. Right, good, good, Jasim. No, E is equal to MC square is not, right? It is energy mass equivalence, right? Right, and in Bohr model, obviously the energy emissions, right? We have two types of spectrum. We have two types of spectra, right? One is emission, another is one is emission, another is absorption spectra. right? Spectra is the plural of spectrum, right? So how many series we learn in the hydrogen case, right? The hydrogen spectrum. So we learn about what? Lyman series. This is important. Lyman series, Balmer series, right? I'll be showing you a slide which has all these topics, right? Then you see we have this nuclei part. In nuclei, we have this isotopes concept, right? I'll be showing you, we have isobars, we have isotones, what is the difference between them, and the binding energy concept that will be studied, right? What are nuclear forces also? This question can also come. And in semiconductors, I have told you this is the p-n junction part is very important, right? What is p-n junction, right? Okay, in p-n junction, we have two types of currents. Can you tell me the name of them? What are the two types of currents we have? Have you heard about one is what are the two types of currents we have in p-n junction? Anyone remembers? So one is no forward and reverse are the biases, right? Those are the biases, right? Forward bias, reverse bias. Currents I'm asking in p-n junction. So we have now you will remember displacement conduction. No, it is not displacement. Yes, Justin, you are correct, right? Displacement current is in the electromagnetic waves chapter, right? In the case of capacitance, in the case of capacitors, right? So it is drift current and diffusion current. Good. It is drift current and diffusion. These are the two types of currents we have, right? Then we need to know about the depletion region. So I'm just from this presentation, I'm just talking about the important concepts you'll be covering, right? In the next presentation, the next slides, I'll be showing you the content part also, right? For you to revise. So this is the depletion region. So depletion region is important. What do we mean by the depletion region? What is its concept, right? Also, in relation to depletion region, we have this concept of potential barrier, right? And to reduce this potential barrier, what we do? We do forward bias, right? And to increase the potential barrier, what we do? Reverse bias, right? So what is the meaning of them? That you need to know, right? Earlier there was Zener diode also, but now the Zener diode has been deleted. So you need not worry about it, right? So the most important thing I told you previously also that previous year questions like CBSC previous year questions are very important. So we'll be covering it in today's class with regards to modern physics, this webinar, right? And chapter wise weightage you must know as I have already told you, right? Okay, now I'll be sharing another presentation with you. All right. So now, is it visible? The screen is visible, I hope. Can anyone tell me if the screen is visible or not? All right. So let us discuss about the dual nature first, right? So in dual nature, what we have these concepts of work function, right? So what is work function? What is work function? So you see here, work function is the minimum amount of energy that we need, right? So it is the minimum amount of energy that we need for an electron to just escape from the metal surface, right? So that is known as the work function, right? So this definition of work function might come in your exam, right? Then we have electron emission, right? So that is the concept of work function only. So electron can be emitted by three methods, right? You must have learnt about this in your NCERT. So one is thermionic emission. What is thermionic emission? When electrons are emitted with the help of thermal energy, right? We heat the metal and electrons are emitted. They get energy, right? Okay, you tell me, why electrons are getting emitted? Why we need to provide energy for the electrons to get emitted from the surface? Can you tell me? Why is it so that we need to provide energy from outside for the electrons to escape the metal? Because the electrons are bound by what? The electrons are bound by the ions, right? Right. So thermionic emission is there. Then we have field emission. In field emission, or it is also known as cold cathode. So you just need to know the field emission part, right? So one is field emission. In field emission, what we do? In field emission, the metal surface is subjected to a very high electric field. So that electric field is responsible for the electrons to get emitted. And then, right, the point of concern that what we have, the point which is important for us is that electrons, photoelectric emissions. What is photoelectric emission? That the metal surface is incident with some radiation, right? And that radiation is having some energy. That energy of the radiation gets transferred to the electron and the electron gets ejected, right? So that is known as photoelectric emission. So in this chapter, we study about photoelectric emission only. Got it? Right? So now you see the photoelectric effect. So what is the definition of photoelectric effect that might come in your exam? The phenomenon of emission of electrons from the surface of substances, right? So when they are exposed to electromagnetic, you see the electromagnetic radiation, right? Sorry, electromagnetic radiations of suitable frequency. What do you mean by suitable frequency? Because there is a concept of threshold frequency, right? So below that frequency, if a radiation is having a frequency below threshold frequency of a metal, then the electrons will not get ejected, right? The photoelectric effect will not take place. So that is the concept of threshold frequency or threshold wavelength, right? And the electrons which get emitted, which get ejected from the metal surface are known as what? Photoelectrons. Why they're called photoelectrons? Because they're emitted due to the incidence of a radiation. And radiation is having what? Photons. Due to the photons, the electrons are getting emitted. That is why photoelectrons, right? This equation is very important. You see Kmax is equal to EV naught. What is EV naught? EV naught is? What is EV naught here? What is V naught here? Can anyone tell me?
Stopping potential.
Yeah, it is the stopping potential, right? It is the stopping potential. So K max is always equal to E into V naught. So this is the important equation which you will be needing, right, in your exam. So K max is equal to EV naught is equal to H nu minus phi naught. So this equation is known as the Einstein's photoelectric equation. Very important, right? This is the whole crux of the photoelectric effect. And then these diagrams, right? These diagrams are important. So this is the diagram I'm having with respect to stopping potential and the frequency. You see, this is the diagram between, let me just, right? So this diagram between stopping potential and the frequency of radiation. So as I'll increase the frequency, right? You see, as I'll increase the frequency, stopping potential, you see, no, this is the equation E V naught is equal to H nu by phi naught. So this is V naught. What is frequency? Frequency is nu, right? This quantity. So this is the graph between them. So what kind of equation it is having, right? So I can have this equation, no, V naught is equal to H nu by E minus phi naught by E, right? So what kind of equation I'm having? I'm having Y is equal to mx plus C type of equation. This is the equation of a straight line, right? What is the slope of these lines? Can anyone tell me? What is the slope of this line? Slope is what? Do you think that if this angle is theta, this angle is also theta? Different metals, they are different metals. So their work function might be different, right? But the slope is same. What is the slope here? Tan theta. What is tan theta? Tan theta is H by E in this case, right? M. You see, X on the x-axis we have frequency nu, and H by E is our slope. By getting it? Yeah, good, Jasim. Good. Very good. H by E. Right? So this graph is very important, right? With respect to stopping potential and frequency, right? So as we increase the frequency of incident radiation, right? As frequency gets increased, maximum kinetic energy gets increased. And as maximum kinetic energy gets increased, the stopping potential gets increased, right? Got it? All right. So let's move forward. Then we have laws of photoelectric effect, right? So these two are from NCRT only, right? These two diagrams are even are also important. These three diagrams, right? Stopping potential versus frequency, and these two diagrams, these are very important, right? So you see, what are the laws of photoelectric effect? So the number of photoelectrons emitted is proportional to the intensity of incident radiation, right? What do you mean by intensity? Can anyone tell me? How can I increase the intensity of radiation? How can one increase the intensity? By bringing the source closer to the metal plate, right? If I'll bring the source closer, then the intensity will increase. And if I'm increasing the intensity, that means what is increasing? The number of photons incident on the metal surface is increasing per second, right? The number of photons striking the metal surface per second is increasing. And if the number of photons increases, then the number of photoelectrons will also get increased, right? So as we increase the intensity, photocurrent gets increased, right? Now we have this threshold frequency concept. So this is the definition of it. You can read, please, right? Then we have this thing that for a radiation of frequency higher than threshold frequency, What is maximum kinetic energy? Maximum kinetic energy is directly proportional to the frequency of incident radiation. So as I'll increase the frequency of incident radiation, the K max will increase, right? And photoelectric emission is what? It is an instantaneous process. It is not as photon strikes, electron gets emitted. There'll not be a time lag between the two, right? So you need to understand these diagrams. You see, this is the collector plate potential, right? So in the diagrams, we have two types of plates, right? One is called cathode, one is anode. So this is known as collector, right? This is known as emitter, right? And here the incident radiation comes, so electrons gets emitted out of it. So as incident radiation come, electrons get emitted. Electrons starts to move towards the collector plate. So collector plate is generally kept at a positive potential with respect to cathode. So as it is kept at positive potential, electrons get attracted towards it, right? And thereby photocurrent gets formed. Getting it? Now, if I'll put it at a negative potential, if I'll keep collector plate at a negative potential, you see here that we have done here only, no, to calculate the stopping potential. Here in this graph, here the potential is kept as negative. It is kept as negative. So now electrons get repelled, right? Electrons get repelled. So they feel a retarding force. And as I increase this negative potential, if I'll keep on increasing it, right? If I'll keep on increasing it, what happens? The electron having maximum kinetic energy also gets retarded and not able to reach the collector plate, right? And thereby we say that the stopping potential has been achieved. So you see, right? But stopping potential is not dependent upon the intensity. This I1, I2, I3 are the intensities. So as I increase the intensity, you see current is getting increased. Saturation, this is no saturation current. It is getting increased. But the stopping potential is same, right? So as I increase the intensity without changing the frequency, stopping potential will not change. Stopping potential will only change when there will be a change in frequency. Getting it? So that diagram also is important. That is not in there in the presentation. The diagram of collector plate and emitter plate, right? That diagram from the NCERT is also important, right? But you see here, as we increase the frequency, right? As we increase the frequency, nu 3 is more than nu 2. As we increase the frequency, the stopping potential also increases, right? The stopping potential, you see, no, stopping potential is greater for more frequency. But for intensities, stopping potential is the same. Okay, so changing the intensity will not change the stopping potential, but changing the frequency changes the stopping potential. Right? Here, stopping potential is more than here, than here. Got it? All right. So let's move on to our next slide. So this is all about the Einstein's theory, right? Einstein's theory of photoelectric effect. So the important equations, which are the important equations? Let me tell you that. So you see, so this is the main point of photoelectric effect. That when radiation of frequencies incident on metal surface, it is absorbed in the form of what? Discrete packets of energy, and those discrete packets of energy are known as quanta or photons, right? Getting it? And this is very important. Einstein's photoelectric equation, which is Ke, right? Or we can say K max, right? This way we can say, right? K max is what? that K max is equal to what? K max is equal to H nu minus phi naught. This equation. And what is this K max? K max can be written as half mass of the electron into maximum speed, maximum velocity, half mv max square, right? This way we can write. And this K max is only, this K max is only equal to what? The charge on the electron and the stopping potential EV naught. So these two equations, first and second, are the crux of this topic, photoelectric effect, right? Any question up to here, right? Up till here, any question? You see, from these two equations, numerical will come. One numerical will come. Definitely it will come. And one question will come from the graphs we discussed above, right? So these two equations you must be thorough with, right? And the graphs which we have discussed above, right? Okay. Then we have dual nature of matter, right? So matter also behaves as waves that we have discussed, right? Matter behaves as waves. So in this, what we have, so it is from where it comes? It comes from the principle of symmetry, right? De Broglie suggested that nature has symmetry. So as radiation can behave like two ways, radiation can behave as a wave also. Like how light behaves as wave? From where do we get to know that light behaves as wave? We get to know this from the phenomena of diffraction. Light shows phenomenon of diffraction, interference, polarization, right? So this shows that light behaves as a wave, right? And when light shows this effect, photoelectric effect, this Compton effect, Compton scattering is there. It is related to the X-rays, right? So that shows that light has particle nature. So as light being a radiation is showing two behaviors, wave behavior and particle behavior. Same way, the matter can also show two behaviors. That's what de Broglie suggested. So matter obviously is made up of particles. So it is showing particle behavior. So it is showing only, no. So it is showing wave behavior also. That de Broglie suggested, right? And he also proved it, right? The Davison and German experiment, which was there previously in the previous year, that demonstrates, right? Okay, Syed, yes, I can explain K is equal to EV, right? Okay, just give me some time. So, right, so matter behaves as a wave, and those waves are known as what? Those waves are known as matter waves. So when we are running, right, when a truck is moving, a car is moving with a speed, so that movement in itself is a wave. That was de Broglie suggesting. But we are not but we do not see it in that pattern, right? Because the wavelength is very less in that case, right? You see, wavelength is very less, right? So in this wave pattern, we gets realized this wave pattern. The observation of this wave pattern is observed in the subatomic particles, which have very low mass. So you see, lambda is what? Lambda is h by mv, right? So mass is important. So we have greater mass than the electron, right? We have very high mass as compared to the electron. So when electron's mass is there, right, then we'll get a high lambda, which can be observed, right? So this pattern can be observed, which we cannot observe in our daily life, right? But yes, matter behaves as a wave, right? So when we walk as a particle also, and we are moving as a wave also, right? Okay. So I told me to explain this. So said it is K max is equal to E into V naught, right? So K max is the maximum kinetic energy of an electron, right? From this equation, which we get. This is the energy of the incident radiation minus the work function. So the subtraction of it, the remaining, if the incident radiation's energy, right, if you subtract work function from it, right, the threshold energy from it, then what we'll get? We'll get the maximum kinetic energy that an electron can have. And what do you mean by stopping potential? Stopping potential is the potential which stops the electron having maximum kinetic energy. Right? Stopping potential is the potential, like it is the negative potential which we apply to the collector plate. You remember in the previous diagram, right? It's a negative potential we apply to the collector plate, right? And that negative potential should stop what? Should stop even the electron having maximum kinetic energy. So that is why we relate K max with stopping potential, right? They have a linear equation, right? You see, K max is equal to EV naught. E is the charge on the electron. It is having same value 1.6 into 10 to the power minus 19 coulomb. That is E. And V naught is the stopping potential and K max is the maximum kinetic energy that an electron can have in a photoelectric effect. Right?
Okay, sir, got it.
All right. Now this is important, right? This you can have screenshot or I'll ask the team to upload this in the system, right? So that you can view these formulae, right? So this is the de Broglie wavelength of an electron, right? So wavelength of an electron accelerated through a potential, right? So there comes this questions that there is a potential difference. There's a potential difference V, and this is an electron, right? So it is accelerated through this potential difference. So can you tell me if an electron is accelerated, if an electron starts from here, from rest, let's say, right? So if it gets accelerated through this potential difference, this electron will get some kinetic energy here, right? It will be having some kinetic energy here. So when an electron moves from this terminal to this terminal, it will move naturally. So this should be at higher potential or lower potential than this. Can you tell me? Let's say this point is A, this point is B. Which must be at higher potential or lower potential for an electron to get accelerated in moving from A to B? A is lower, right? Good. Because electron travels naturally from lower potential to higher potential, right? Electron is a negatively charged particle, right? So A is at lower potential. So potential at A is lower than potential at B, right? So that is why it will get repelled. No, this is negative potential, this is positive potential, you can say. As we say in case of battery, right? This is higher potential, this is lower potential. So you see, it will go towards the higher potential and it will get accelerated. It will get a kinetic energy, right? So if I get this, if I have been given this potential difference, I know the value of E, I know the value of M, right? So I can calculate the lambda associated with it. So that formula comes out to be this 12.3 upon under root V angstrom. So this value comes in angstrom, right? What is angstrom? Angstrom is 10 to the power minus 10.
Excuse me,
Right?
sir.
Yeah.
So could you please explain how did we change the denominator from MV to what is written over there?
That's what I'm saying. No, we have put the values here, right? We have put the values of H. What is the value of H?
No, no, no,
6.8.
no. My doubt is not that, sir. My
Uh-huh.
doubt is how are we changing MV to root 2 MEV?
Okay, okay, okay. This you're asking. Okay, okay. Let me tell you this. So see, what is happening here? Well, lambda is equal to H by P. Got it? Right?
Yes, sir.
So when a charged particle, let's say an electron is having how much charge? E charge, right? So when a charged particle moves through a potential difference, the charged particle gets a kinetic energy here, right? And that kinetic
Yes, sir.
energy is equal to how much? E into V, right? That
Yes, sir.
kinetic energy is E into V. If generally we calculate for a Q part, no. So this is the potential difference.
Okay, got it, sir.
How much you must have studied this in electrostatics, right? So how much kinetic energy it gets? Q into V, right? And we know that what is kinetic energy? Kinetic energy is half mv square, right? So let's divide it by m and multiply it by m. So this is m square v square. So I can write it as p square by 2m. P is the momentum, right? So I can write p as what? I can write p as under root of 2m into kinetic energy. And now kinetic energy can be written as E into V. Got it? So it
Got
is
it, sir.
under root
Yes.
2m EV. Okay. Then next we have de Broglie wavelength associated with the particle momentum P. So that we know h by p, h by mv, right? And also it can be written in nanometer as like this. It is the same thing, right? It is angstrom, right? We have just put decimal point to the left, so it becomes nanometer, right? So this formula is important in terms of nanometer, right? Okay, then let's move ahead. So then comes to the chapter of atoms. So in atoms, so the purpose of these slides are to just have your revision of the chapters, right? So atoms. So in atoms, what we discuss? In atoms, we discuss the Rutherford's model, right? The Rutherford's model. So what is important here? The Rutherford model is in itself important. The results of the experiments, right? So through the results of the experiments performed by Giger and Marsden, so they performed the experiments, and the results and when the results came, those results were like analyzed by the Rutherford, and he proposed the following model, right? So these points are important. So you can get a theory question of like 2 marks or something, that what is the Rutherford models of an atom, right? So you need to tell these points, that an atom consists of a small and massive central core in which the entire positive charge and almost the whole mass of the atom are concentrated, right? So this is known as nucleus. And nucleus occupies a very small space as compared to the size of the atom. So that means most of the atom is empty, right? That you need to tell. The electrical neutrality part you should tell. And electrons revolve around the nucleus. That what Rutherford said, right? The centripetal force point you can say is required, right, for the revolution of the electrons around the nucleus, right? So the point is that you need to learn this Rutherford's model wale points, right? Then next, most importantly, this 2024 exam paper, this question came, drawback of Rutherford's model. What is the drawback of Rutherford's model? This also comes, right? So what is the main drawback? He could not explain the stability of the atom, right? So you need to write as as word by word, right? As it is written here. As according to classical electromagnetic theory, the electron revolving around the nucleus must continuously radiate energy revolving around the nucleus, right? In the form of electromagnetic radiation, and hence it should fall into the nucleus, right? So the point is that, as Rutherford said, that the electron is revolving around the nucleus, right? So if something is revolving around the nucleus, so it is accelerated, right? If something is in a circular motion, it is revolving, that means it is in circular motion. So it must be having centripetal acceleration. So it is accelerated. And an accelerated charge. So there is a concept in classical electromagnetic theory, right? And that's why came the quantum theory, no? That's why Bohr suggested the quantum theory in relation to the atomic model, right? Because according to the classical theory, this was not being explained, that an accelerated charge, if a charge is accelerated, no, this is the concept of EM waves also, right? EM waves also tells this, that an accelerated charge, what it does, it radiates radiation, it radiates energy. And if the energy is getting radiated, that means there's a loss of energy is happening. And the loss of energy is happening, ultimately the electron will get into what? The nucleus, and the atom will get destroyed, right? So he could not explain that, right? That why it is stable even then. Okay, being accelerated also, why it is stable. Then Bohr suggested no, that there are stable atomic orbits, that there are some orbits which are stable, in which electron does not radiate energy, does not lose out energy, even while revolving around the nucleus. Getting it? This is important because it just came in the previous year exam, right? Then generally you get this question also, this distance of closest approach, right? Distance of closest approach. What does it mean? It comes from the alpha particle scattering experiment, right? When alpha particles are bombarded, right? They are like thrown at the gold atom, right? Gold nucleus. So do they really strike them? Right? Let's say this is a gold nucleus, right? And an alpha particle is coming. This alpha particle is coming. What do you think? This alpha particle, it is positive, right? Alpha particle is positive. And this nucleus is also positive or negative? What? Nucleus is also positive, right? So do you think this alpha particle really strikes the nucleus? It does not strike it, right? Because positive charges get repelled. So it goes close to it and get repelled like this. This way the scattering is happening. So this distance is known as the distance of closest approach, right? How much closest the alpha particle is going towards the atomic, the gold nucleus. You're getting it, right? So this is the formula. Sometimes numerical comes, and there's a numerical in NCERT also, right? Of distance of closest approach. So what we do, by alpha particle is coming with some velocity. You see, alpha particle is coming with some velocity. So that velocity means the kinetic energy it is having, half mv square. And when it stops, because alpha particle stops at a point, no, it stops here and then gets repelled, right? So when it stops here and there is the nucleus, right? Both are positive. So this kinetic energy, this kinetic energy alpha particle starts with, this kinetic energy, this half mv square gets converted into what? Potential energy. And what is that potential energy? You see, what is potential energy in electrostatics? K Q1 Q2 by R. You see, this is K. What is Q1? Q1 is the charge on the alpha particle, which is 2 into E, right? Alpha particle is having helium 2 plus, right? This is alpha particle. And what is the positive charge we are having here? Let's say its atomic number is Z. So it is having what charge? Z into E, because it is having Z number of protons, right? So 2Z square upon this, upon D. So D is the closest approach, right? So from here, I'll get the value of D as like this. This is the value of D we get. By getting it? What happens to M and V here? No, M and V, they are that is written as K, kinetic energy. This K is kinetic energy, right? So you can put half mv square also, but you can put that as kinetic energy, right? Okay, so let's move forward, right? Then we have this concept of quantization or discretization, which is known as what does it say? The concept of quantization. It says that anything cannot vary continuously, right? But can change only discontinuously. It can have some specific values, right? The way electron has some specific, the energy of the electron can have only some specific values in the case of Bohr's model. It can move in only certain orbits, right? So that is what the quantum condition, right? You see here, Bohr's postulates, that is important. That question comes every year, right? Postulate of Bohr's model, 2 marks or 1 mark even, right? So quantum condition is what? That the angular momentum wala, that point, right? The angular momentum of an electron must be what? The integral multiples. The integral multiple of h by 2 pi, right? So this concept, so this is important, right? This formula is important. And what is the angular momentum? It is MVR. So MVR is equal to NH by 2 pi. N can have 1, 2, 3. So this is the quantum condition, that angular momentum of an electron in an atom can have only these values. H by 2 pi, right? 2H by 2 pi, 3H by 2 pi. It can have only these values. It cannot have this value, 1.5H by 2 pi. It cannot have this value, right? It cannot have this value, 1.23H by 2 pi, right? It cannot have this value. So that is the meaning of quantization, right? Only specific values, only some discontinuous values are allowed. Got it? So this postulate you must write if it comes. Then we have stationary orbits. The stationary orbits are what? These are the non-radiating orbits, right? That's what Bohr suggested. That these are the permissible orbits. That when an electron orbits, when an electron revolves in these orbits, it will not radiate energy, right? Then we have this frequency condition. This postulate you must write frequency condition and the angular momentum. These two postulates are important, right? This one is important, frequency condition. So it says that when an electron jumps from a higher to a lower orbit, what it does, or from a lower to higher orbit also it can go, right? So if it jumps from higher to lower, it will radiate energy, right? It will radiate energy. And if it goes from lower to higher, it will absorb energy, right? So how can we calculate the energy difference? How can we calculate the frequency of the emitted radiation or the absorbed radiation? How can we calculate it? We can calculate by the energy difference between the orbits, right? E2 minus E1 should be equal to h nu, right? Then we have this radius of the orbit. This is the formula. This you need not mug up, right? You need not mug it up. Just know the concept behind it, right? How we calculate it? We calculate it by these two formulas. MVR is equal to NH by 2 pi. This one. So one equation is this. You just remember it. And the second equation, which is important, is what? The centripetal force one. What is the centripetal force? Centripetal force is mv square by r. This is the centripetal force, which is equal to what? 1 upon 4 pi epsilon naught, right? What is the Coulomb force? K Q1 Q2 by r square. So what is Q1? Charge on the electron, which is E. What is the charge on the nucleus? Z into E upon r square, right? So these two equations are important. With these two equations only, you can solve any question of atoms, right? With respect to radius, with respect to velocity, right? All right. So let us move forward then. Right. So this is the equation for just this. You must be knowing that kinetic energy and potential energy you must be knowing, right? And also you see here the relation between them. Kinetic energy is E square by 8 pi epsilon naught r. Potential energy is minus of E square by 4 pi epsilon naught r. Which is greater? Potential or kinetic energy? Potential energy is greater, right? So I can write what? What is potential? Potential energy is minus twice of kinetic energy. Can I say that? Right? And you see what is total energy? Total energy is kinetic energy plus potential energy. Right? So if I'll calculate total energy, which is K plus U, right? And I can write U as what? Minus 2K. What is total energy? Total energy is minus K only. Minus of E square by 857 R. Right? This minus 27.2 by N square EV. That is a different formula, right? I'll just let you know. I'll just let you know this one. Okay. Then we have this concept of speed of an electron, right? You see, one important thing is here. Sometimes question may come from here, right? The speed of an electron in the nth orbit, right? You remember it like this. It is V is equal to 1 by, you see, 1 by 137 into C by N, right? C is the speed of light. Now, what is 1 by 137? 1 by 137 is known as alpha, right? Which is known as fine structure constant. This is given in NCERT, so this might come. In MCQs, this might come, right? What is the value of fine structure constant? So you must be knowing 1 by 137, right? Okay. So then you need to know the failure, right? Failure of Bohr's model. So Bohr's model, what is the failure? What are the limitations we can say? What are the limitations of Bohr's model? Limitations are that it is applicable to only hydrogen-like atoms, right? It is not applicable to the atoms which have more than one electron. It fails in case of higher atoms, right? And also it cannot explain the fine structure of spectral lines. There's a fine structure also that we will be doing in your higher studies, right? So it cannot explain that, the fine structure of the spectral lines in the spectrum of hydrogen atom, right? Okay. Then the energy level diagram is important. Spectral series of hydrogen atom is important. That what happens when an electron makes a transition from a higher energy level to a lower energy level, right? So this is the formula which we get, right? If we want to know the frequency of the radiation emitted, right? So that we must be knowing. So you see this diagram is important, right? So what do you understand by this diagram? Can you tell me? You see, so this is what? This is which series? This is the Lyman series, right? You see, this is the hydrogen energy levels we have. This is the first energy level, ground state of hydrogen. What energy it is having? Yes, the energy is released, right? Right. So, so it is having minus 13, right? Minus 13.6 electron volt. It has, right? So you see, this is the Lyman series, right? So n is equal to 1 is the ground state. So an electron can come to n is equal to 1 from n is equal to 2 also. It can come directly from n is equal to 3 also. It can come from n is equal to 4 also. It can come from n is equal to 5 also. So, so these different transitions, right, emit different frequencies of radiations, right? If an electron jumps from 2 to 1, it will have different frequency. It will, if it will transit from 3 to 1, then it will have different frequency because the energy levels is different, right? What is the frequency of radiation? How can we calculate it? H nu I can calculate as difference in the energy levels, right? So frequency you see is directly proportional to the energy difference. So now can you tell me which is having the lowest frequency? Which transition is having the lowest frequency in Lyman series? 2 to 1, 3 to 1, 4 to 1, or infinity to 1? What do you say? So it is what it is. You see, where's the energy difference lowest? Energy difference is lowest between n is equal to 2 to n is equal to 1. Right? So with regard to this transition, the frequency is the lowest. Right? But wavelength is maximum. Right? Then we have Balmer series. In Balmer series, it is n is equal to 2. Right? So electron gets transition from 3 to 2, 4 to 2, 5 to 2, like this. Then we have Paschen series, where 3 is the limit, lower limit, right? So we can have transition of 4 to 3, 5 to 3, 6 to 3. Then bracket series, where n is equal to 4 is the lower limit. And then we have P-fund series, where n is equal to 5 is the lower limit, right? So this diagram is important to know the what is Balmer series, what is Paschen series, right? And these are the different characteristics of these series. You see, the Lyman series is what? When an electron jumps from n is equal to 2, 3, 4 to n is equal to 1, right? Then we get Lyman series. And in which region it is? This might come in your MCQs, in your board exams. Which region? It is an ultraviolet region, right? The frequencies which we get in Lyman series, the wavelengths which we get in Lyman series are from the ultraviolet region of the radiation spectrum, right? Then we have Balmer series. Balmer series is when electron jumps from 3, 4, 5, anywhere to n is equal to 2 orbit, right? Okay, then we get Balmer series when n is equal to 2 is the lower limit, lower state, right? And where these frequencies, so the frequencies emitted come under which region? It comes under visible region, right? The Balmer series comes under visible region. And then Paschen series, bracket series, P-fund series all come under which region? Infrared region, right? All come under infrared region, right? Then I have this formula of Rydberg constant. Please have a look at it. What is this 1 by lambda? 1 by lambda is known as wave number, right? You see, 1 by lambda is known as wave number, right? And this equation can be written as like this, right? 1 by, I can write it again for it is not clear, I think. So 1 by lambda is written as like this, R. So this quantity, M, is e की power 4 upon, right, 8 epsilon naught square CH cube. So 1 by lambda for any hydrogen-like atom. For any hydrogen-like atom, it can be written as like this, R Z square 1 upon N1 square minus 1 upon N2 square, right? Where R is what? R is known as the Rydberg constant, and it is having this value 1.097 into 10 to the power 7 per meter, right? And if it is a hydrogen atom, then you put for hydrogen atom, you put Z is equal to 1. When you put Z is equal to 1, you will get 1 by lambda as R 1 by N1 square minus 1 by N2 square, and then you can put different values. If I'll say for Lyman series, you will put N1 as 1 and N2 can take any values from 2 to infinity, 2, 3, 4, 5, 6. Getting it? Right? Then lastly, as time is not much, so this is nuclei. My whole point is to make you like revise it the way we are revising. Just focus on the important formulae, right? The important formulae. There are no derivations from it, right? There are no derivations in this dual nature. There are no derivations in modern physics, right? So derivations you need not worry about in modern physics. In modern physics, you just need to focus on the theory part, right? And the diagrams part, right? For example, the diagrams in photoelectric effect, the graphs in photoelectric effect are very important, right? So this is about now nuclei. Let me discuss it as I've started. Right? So what is atomic number? Atomic number is the number of protons. It is denoted by what? Z. What is mass number? Mass number is denoted by A. It is the number of nucleons. Nucleons means protons plus neutrons. That is mass number. Right? So what is number of protons? Z. Number of electrons? Z. Because electrons must be equal to number of protons in an atom, right? In a neutral atom. All right. Number of nucleons is what? A. If I want to find number of neutrons, sometimes this question might come in MCQs, right? You are given A, you are given Z. So, and you are asked number of neutrons. What is number of neutrons then? A minus Z. Got it? Then isotopes. What are isotopes? Isotopes definition might come. So, isotopes are the atoms of an element which have the same atomic number, right? But different mass number. So, they have the same atomic number, but different mass number. So, that means what? They have same number of protons, but different number of nucleons. So, that means different number of nucleons, but different number of neutrons they have. Right? So isotopes have similar chemical properties but different physical properties. Right? Now, what are isobars? So these definitions also might come. Isobars, isotones. Isobars are same mass number but different atomic number. Reverse of it. Isotones are nucleides means nuclei. Same thing. So isotones are having same number of neutrons. Right? Those are isotones. Isomers, same atomic number, same mass number, but different energy states. Those are isomers. But you need to worry about only isotopes, isobars, and isotones. Right? What is electron volt? You already know electron volt is the energy acquired by an electron when it is accelerated through a potential difference of 1 volt. Right? Just we studied it. Right? Then if an electron gets accelerated through a potential difference, it acquires kinetic energy. So if it is accelerated through 1 volt potential difference, then the energy it acquires is known as 1 electron volt. Right? Now, this is important, right? This part is important. Every year question comes, right? The radius. So the radius of a nucleus is proportional to the mass number to the power 1 by 3. You see, so R is equal to R naught A ki power 1 by 3. And R naught is having this value. R naught is a constant, right? Right? So what does it mean? It means that volume of a nucleus is what? 4 by 3 pi r cube, right? So R is this. So what is volume? 4 by 3 pi r naught cube into A. So you see, volume is proportional to the mass number, right? The A. And the density of the nucleus is what? The density of the nucleus is constant. Any nucleus in this universe of any element, the density remains constant. Density is independent of A. This concept is important, right? For all nuclei. And density of nucleus is very high. You see, 2.3 to 10 to the power 17. The density of water is 10 to the power 3, right? Water we experience every day. But it is much more than that, much more than that, right? Very large, 10 to the power 17. So that's what we studied also, no? That the nucleus is very dense, right? So this part of the nucleus is important, right? You keep in your mind. Right? So there are various topics, more topics, right? So I'll be sharing this PPT and the other materials with you, right? The team will share it so you can go through it. And you might be already having your notes, the NCRTs and all. My point is just to have a quick revision of every concept. And when you'll be coming for the next webinar, you please let me know the questions from it or any doubts you're having, right? And still, I'll be available for questions, right? So if you'll be having any questions related to any topic and the strategy to go about in modern physics, you can discuss, right? So you'll have to study this mass defect, this binding energy, right? This is important, right? Then we have this nuclear density part, right? That we have already done, right? Then this graph is also there, but this graph you need not remember or nothing else. Just this is with relation to fission and fusion concept, right? Earlier it was important, not right now, right? But you need to study it. You need to analyze it, right? In the nuclear part, right? Also, I have one sheet of this semiconductor electronics. In semiconductor electronics, you just let me just show you very quickly. Visible? Can anyone tell me? The semiconductor
Yes, sir.
electronics. All right, all right. Just very fast. I'm just letting you know the topics, right? So intrinsic semiconductor is important, right? Intrinsic semiconductor. What is the difference between intrinsic semiconductor and extrinsic semiconductor, right? That you must be knowing, right? Then in extrinsic semiconductors, we have two types of conductors, N-type and P-type, right? In N-type semiconductors, which are the majority carriers? Majority carriers are the electrons, right? Holes are the minority carriers, right? The concentration of electrons is much greater than the concentration of holes. In P-type semiconductors, what we do, we put trivalent impurity. In N-type semiconductors, what we put pentavalent impurity. So this difference between N-type and P-type, you should be very clear of, right? This will come. So two things I'm saying, intrinsic and extrinsic difference and N-type and P-type difference, right? So this question will come, right? No need to remember these energy bands, right? This band diagrams, these are, right? But if you know already, that's good, right? Then this question might come, the electrical conductivity of a semiconductor. Because in a semiconductor, we have current due to majority carriers also, we have current due to minority carriers also, right? So in this case, the current becomes what? You remember the current is what? You remember the current is what? You remember current is what? J is equal to NEVD. VD is the drift velocity, right? And J is current density. So I comes out to be NE area of the conductor into VD, right? So here, what is there? You see E into A, NE into VE, and NH into VH, because both the currents are there due to electrons also, due to holes also. That is why we are having both the currents, right? All right. So then forward, what is forward biasing? What is reverse biasing? That you should be knowing in PN junction, right? What is forward biasing? What is reverse biasing? You should be able to draw the diagram, right? That's all. Transistor is not there, nothing is there. So these points you must keep in your mind, right? So I hope I have been able to cover the maximum what I can in the limited time, right? So if you have any question, right, I am available. No, no, no. Rectifiers, yes, rectifier diode as a rectifier might come, right? I'll just confirm you in the next webinar. Jasim, you please join it. So this webinar has been helpful or not? What do you think, Jasim? It has been helpful to you or not? Right. So it is a quick revision, right? That's what the whole concept of it, right? Just one shot revision, the quick revision. You just So you might have studied it long before, or you might be planning to study it, right? So now if you'll study it, you will get it like with much more clarity, and you'll be able to figure out the core topics, which is the whole point we are discussing here, that the core topics should be focused upon, right? So if you have any question, right, the time is up for the webinar, but I'll be taking your questions. So if you have any question, the participants, if you're having any question, I am here. Otherwise, you can please leave the meeting and keep studying, right? And very just focus on the core topics, right? Just focus on the core topics which must be coming in the exam, and focus on previous year papers, right? So there'll be a webinar for previous year paper also. In that webinar, I'll be discussing the whole paper, right, for the whole various topics, right? So you please check on the schedule for the next webinar and do attend it. It will be much more helpful, right? We'll be doing some questions also, because this part was theoretical. So that's why we have not been able to do much numericals, and the time is also limited. But the point to take home is the core concepts, right? Focusing on the core concepts and just keeping yourself calm and composed at this time of just last phase of your preparation. All right, thank you from my side. So any questions? Otherwise, you can leave the meeting. Okay, Jasim, thank you. Thank you.